Welcome to Summarize Science, where we break down the latest breakthroughs in technology. Today, we are looking at a fascinating new tool called BrickSim, designed to help robots master the art of building with interlocking bricks. While playing with toy bricks seems simple to us, it is actually a massive challenge for robotic systems to understand how they snap together. Most standard physics simulators are great at modeling solid objects, but they often fail when it comes to the tiny friction and elastic forces inside a brick connection. As you can see here, traditional simulators like MuJoCo often see a perfectly stable brick structure spontaneously collapse. This is because they don't truly understand the snap-fit mechanics that keep the studs and holes locked together. Without a better way to simulate these forces, it is nearly impossible to train robots to build complex structures efficiently. That is where BrickSim comes in as the first real-time, physics-based simulator specifically for these assemblies. The researchers created a system that can simulate assembly, disassembly, and even structural failure with incredible detail. It achieves this by using a hybrid architecture that delegates general movement to a standard engine while handling the brick connections separately. The core of the system is something called the brick topology graph, which tracks how every single brick is connected. This graph allows the simulator to maintain the correct relative positions of the bricks without the numerical drift that often ruins other simulations. It also uses an assembly monitor to detect when a robot is successfully pressing a new brick into place. A breakage detector constantly runs in the background to calculate if the internal forces are too much for the plastic to handle. The physics model is quite detailed, accounting for the different contact points between a stud and a hole. It calculates 3 different types of forces: the radial force of the snap fit, the axial force along the stud, and the friction that resists twisting. For the simulation to accept a connection, the bricks must align within very specific geometric tolerances. There also has to be enough physical pressure applied by the robot to actually click the pieces together. When it comes to testing, the results are quite impressive compared to previous methods. On a test set of 150 real-world assemblies, BrickSim predicted static stability with 100% accuracy. It is also incredibly fast, with an average solve time of just 5 milliseconds per frame. This speed is vital because it allows the simulator to run in real time alongside modern robotic control pipelines. The simulator also shines in dynamic drop tests where structures are let go from a height. In these tests, BrickSim was able to precisely mirror real-world results, identifying exactly which connections would break upon impact. You can see how the simulated bench and guitar structures split apart in the exact same locations as the real physical models. Most of the computation happens so quickly that the simulation stays well within the limits required for a smooth 60 frames per second. By integrating with NVIDIA's Isaac Sim, BrickSim can support a wide variety of robotic platforms like these Franca arms. It allows for both single-arm building and bimanual cooperation, where 2 arms work together to snap bricks into place. This creates a safe virtual playground where AI can learn to plan long-term construction tasks without damaging expensive hardware. The code for this project is open source, meaning researchers everywhere can now use it to advance the field of robotic manipulation. To recap, the researchers have developed a high-fidelity simulator that finally masters the tricky physics of interlocking bricks. This means 100% accuracy in stability testing, real-time performance, and a path for robots to learn complex assembly tasks. In the future, this technology could pave the way for autonomous robots that can build furniture or even modular housing units. Thank you for watching Summarize Science, and stay tuned for more deep dives into the world of discovery.